Panel discussion session for today. We're going to discuss the science case or cases for joint observations of LSST and LIGO. So, what's really the science that we can address with joint observations versus individual observations with LSST or LIGO alone? And as usual, we have a couple of panelists here who are going to present some ideas that we're going to discuss. I guess we have like half an hour.
Yeah.
So we, as I guess, started. Do you have the slides up there?
So I have.
So who's going to
slide?
start?
What's the name of the slide that you're looking for?
This slide?
Yeah, which one?
I have no science case.
This one.
Oh yeah.
This is one for codes, but can you send the other slides as well?
Yeah, I think so. I send you Should we get?
Yeah, this one. This one. I got it.
Should we get 40 slides first? What do you want to start?
I think it's better to probably talk after the your talk.
After mine? Okay.
Right.
All right. Okay. Then I'll just.
Because I think I'm talking about that more with radio, not summer stuff. Right?
Okay.
You're probably talking about some radio stuff.
Sounds good. Okay. So I'm gonna start, and I just wanted to come back again to this question of the origin of short Gamma bursts that also Satya has mentioned in his talk already. So. At least from first principle calculations, we still don't really understand how short gamma bursts are produced in neutron star mergers. We do have some indications, at least in the case in which we promptly form a black hole after merger. So there are MHD numerical relativity simulations who indicate that there's a funnel forming and that at least the necessary conditions to launch a relativistic jet are sort of met. But in the case in which we form a long-lived neutron star in such a merger, we still don't really understand on first principles how such a jet can actually be produced or launched. And so this is essentially nicely summarized in this graph. So these are recent simulations that we did in which we collided neutron stars. And in one case, so we chose different equations of state. In one case, we chose an equation of state with a low maximum neutron star mass, and that promptly formed a black hole after merger. And so once this black hole forms, the pressure support essentially stops, and material with low angular momentum in the polar funnel simply accretes onto the black hole and evacuates this sort of polar funnel in which you can at least have some low density region, low baryon pollution, so that you can actually have at least the necessary conditions to launch a relativistic jet. Whereas in the other case, where you form this long-lived neutron star, you have this isotropic baryon pollution that I was also mentioning earlier today. And at least for over the lifetime of this simulation, we don't really see that there's any sort of polar funnel clearing up that could actually produce a baryon poor region for a jet. So there's some problems with trying to understand how short gamma bursts can be produced. There's several ways out of this. One scenario that we proposed a couple of years ago is that maybe this short gamma burst is actually produced much later, not at the time of not at the time of merger, but is rather produced when this long-lived neutron star collapses to a black hole, and that might be after a spin-down timescale, which for typical parameters could be minutes, hours, or maybe even up to days. So my point that I just wanted to make here is that we are not really sure yet when and how short gamma bursts are produced in these mergers, and doing joint observations on the electromagnetic and the gravitational wave side might actually give us some indications and might constrain different theoretical ideas on how short gamma bursts can be produced in neutron star mergers. Simply because scenarios like this have very distinct electromagnetic signatures that we can look for and that we can test, and then once we have observations, we can actually constrain those models. One specific prediction of this model, for example, is that there might actually be some precursor electromagnetic emission prior to the short gamma burst. So where and how this electromagnetic emission manifests itself is still a matter of debate, and we have to come up with better theoretical models for this. But there could be actually an optical or UV precursor, maybe in some cases even an X-ray precursor to the short gamma burst that we might be able to look for with joint observations of LSST and LIGO in the near future, trying to understand better how short gamma bursts can be produced.
But you're talking about minutes or hours or days?
Yeah, that's a very good question.
I mean,
So,
for LSST, if it's minutes, you probably are not looking at the right place at the right time. So,
right. So, well, minutes would be like sort of an extreme case probably. So at least in this scenario where the neutron star has a spin-down timescale to collapse and produce the GRB, it's more on the order of like hours, maybe even up to a day, depending on how strong the magnetic field, for example, is that this neutron star is born with. But these are parameters that we don't exactly know. So there's some uncertainty to this, but typically it could be on the order of hours to days, and so there could be some sort of precursor signal that we might be looking for.
Do you have a chance, so, if you detect the GRB / gravitational wave, order 5 years, that's not going to be sooner, most likely, right? Is there any other way you can test this before that on a shorter time frame, just from electromagnetic, for example?
Well, so it depends a little bit on the exact emission that we're looking for. So it's something that we still need to determine better on theoretical grounds. So where the signal is actually really going to peak and how bright it will be. It could be that there's significant X-ray radiation at the early stages or so. We might be looking at these things with X-ray satellites or so, existing facilities. But it's very hard to catch. So the possibilities are very limited. So the exact timing will be very interesting and will be most constraining. So the gamma rays and the gravitational wave signal, and then hopefully something in between or after that.
What kind of spectrum do you predict for this precursor?
So there's different. So Kota will probably also talk about this a little bit after me. So there's thermal and non-thermal radiation. Yeah, I would predict a strong thermal component, and when I talk about optical UV, it's probably mostly thermal radiation. So energy that is extracted essentially from the central engine, from this neutron star, that is reprocessed by this nebula, is sort of reabsorbed by this outer ejector layer. So this is where the energy essentially becomes thermalized, and this is what essentially provides the thermal spectrum. But then there might be also other types of radiation that is probably higher energies, at higher energies, X-rays or gamma rays might be able to escape because simply the opacities are much lower in those wavelengths. So there might be other non-thermal signals that we might see as well.
But your X-rays will not be thermal.
Yeah. Well, so if this ejector can be actually really heated up to fairly high temperatures, then you can touch like the soft X-rays or so probably, but it still needs to be better understood.
What is the process that transfer the energy from pushing the ejector to thermal energy? What's the mechanism? I mean, I understand if you push something, you give it kinetic energy, but then you have to transfer the kinetic to get radiation. You have to transfer the kinetic energy to thermal energy. Particularly, you're talking about thermal energy. How do you thermalize the kinetic energy?
So in this case, it's not really thermalization of just kinetic energy, but actually what is heating up the ejector and what is, say, thermalizing energy in this ejector layer is this pulsar wind nebula. So what is essentially happening is that you have this neutron star, this fast rotating neutron star that via its pulsar wind feeds, so extracts rotation energy into this pulsar wind.
Pointing flux.
Yeah.
So how do you convert the pointing flux to thermal energy? It's even more difficult.
Okay, well this is like the general problem of pulsar wind nebulae, right? So like
there is a completely different story. There you convert it at very large distances, and you're accelerating particles, and it's a completely different story. Here you want to convert directly pointing flux to thermal energy, and I don't know of a mechanism that does it. So,
well, we're sort of hypothesizing that a pulsar wind nebula like the conventional pulsar wind nebula that we know of, are sort of generated in this system just on different time and length scales, so that you have essentially something like, I don't know, a termination shot, in which you thermalize the Poynting flux into particle energies.
But not summer, right? So the usual pulsar wind nebula, basically the most of the Poynting flux is converted to non-summer particles.
Yes.
Particles are
Yes.
really
So then you have like as in a usual pulsar wind nebula, you have heated up particles that undergo high energy.
And emission in the pulsar is the classical pulsar wind nebula. That is not the classical pulsar wind nebula. This is just the explosion, right, that you're talking about.
This is not an explosion. This is just the ejector material that is ejected during and after the merger on timescales of say tens of milliseconds up to a second or so. That is moving away from that got unbound during this process, and that is moving away from this merger site. And it's just confining this pulsar wind
So
nebula.
how long does it take to go from here to there to there? I mean, it's not like thousands of years. It's just seconds,
Yes.
right?
Well, it's so this is on this whole thing is on the timescale of spin down timescale. So this is from say the shortest is probably like on the order of minutes, and then you go to hours and days.
I mean, I don't think we know how well it thermalizes, but one way you
Yes.
can thermalize it, if you create this nebula, which I agree, we have like some reconnection or some sort of, trap the magnetic field, it undergoes reconnection, you accelerate non-thermal particles, you make non-thermal radiation, and then non-thermal radiation can be absorbed by this
Right.
ejecta, if it's UV or soft X-rays, by bound-free processes, and then that re-emits it as thermal radiation. So there are ways, but it depends on where exactly this nebula is putting its energy. If it's putting it at really high energies, it's just going to leak out.
Right.
And so you have some the presumption is that some fraction of it will be in an energy range where the ejector can absorb it and turn it into something thermal. But there may also be a non-thermal component.
Which is better for you, if it's thermal or non-thermal for observation purposes?
Well, that exactly depends on how these signals would exactly look like, and
If it's thermalized, it's likely to come out in the optical, like
Yeah,
the
yeah.
filament or infrared.
Or
If it's
UV
non-thermal,
or
it can be harder X-rays or
Yeah,
gamma rays. I'm going to guess the hard gamma rays are going to be hard to detect with these luminosities.
Okay.
Depends on whether you have an X-ray satellite or.
So you would prefer optical?
So it's
But-
but I think no summer is sometimes better, right? Because if you want summer, that you have degeneracy, right? You can may not be pulsar or some the energy source can be different, right? Some energy source output might be produced by some different energy, right? If you see the X-ray, the no summer particles, and then maybe you can directly see some internal dispersion.
Sure, in terms of what you learned from it, maybe you learn from it.
So it's not out of the question that this could be like a hard X-ray precursor that you could see with BAT before the short GRB itself.
I don't know at this stage. Probably you cannot rule it out. Yeah.
I guess I'd like to know more about the model for the delayed gamma ray emission. Because I mean, right now in LIGO, I think we're only searching out to like 6 seconds or something.
Right,
when we
1
do it.
second, right? We searched 6 seconds before.
Oh, right, yeah, I had it backwards.
So one before and 5 after, right? Or-
No, I
No,
think
5
everybody
before.
said it's the
Five
other way
before.
around.
Yeah,
Are you
so
sure?
for the precursor, so if you have the gamma ray burst, search for 5 seconds before the gamma ray burst and 1 second afterwards,
Okay.
I think. Because, yeah, so this is the opposite. So we are really, the applicable number is 1 second.
At any rate, it's still way
Yeah.
smaller than minutes or days or hours or
Right.
weeks or whatever. So, I realize, I mean, I guess it sounds like a lot of the problem was saying whether or not it's, okay, so a second wouldn't be bad, it would still kind of fit.
Sure.
A minute would be bad, an hour would be bad. Like, part of it would have to do with like what the time to collapse is, and I realize we don't understand that very well,
Right.
but you must be able to put some prior expectation. Is it more likely to be minutes, or is it more likely to be days, or it can't be uniform, can it?
No.
That would suck.
Yeah, that's a good point. So these short delays are typically expected if you form a what you call a hypermassive neutron star. So and that very much depends on the equation state that we also don't understand. So if you form these short delay times would apply to hypermassive neutron stars or prompt black hole formation, and they would be typically on the timescales of milliseconds, tens of milliseconds, maybe hundreds of milliseconds. So definitely within this window. So the hypermassive neutron star collapses, they should be sort of captured by the usual search window. The problem, I think, is that once you really form a long-lived neutron star, by which I mean like a supermassive neutron star, so that can still be sustained, so that in which the gravitational collapse can still be sustained by solid body rotation to some extent, and so this will spin down via its magnetic field until it has lost like a significant fraction of its rotational energy, and that sets the point of the time of collapse. So now this spin down time scale, so this time scale over which it loses a significant fraction of its rotational energy, depends on the magnetic field via which it spins down. So and this magnetic field is essentially produced during the neutron star merger by magnetohydrodynamic processes. So there's a lot of magnetic field amplification. And we are studying this in simulations, but there's still no consensus, or there's no definite conclusion on what a typical magnetic field strength and topology of the magnetic field after the merger is. So various groups are investigating this. We have some ideas about the magnetic field strength, which is probably on the order of typically 10 to the 15, maybe up to 10 to the 16 Gauss. And so over this range of, say, possible magnetic field strength, if I just plug this into some spin-down formula that predicts this lifetime of the neutron star, this is essentially what then tells us that this has to be somewhat between, say, minutes, a few minutes, and maybe up to days.
The gravitational wave emission, I mean, if it keeps any kind of time-varying quadrupole limit, it'll keep radiating gravitationally too. And I realize that, like with normal pulsars, we say, oh, well, the magnetic is going to be so much more. In fact, we place limits on crabs and crab pulsars and things like that in terms of spin down. But for this thing, like, it's going to be a weird thing. Like, I mean, it's going to have all kinds of weird modes. It might radiate a lot gravitationally for a while, and that might actually dominate the magnetic, right?
Yeah, it might. So that is typically what drives the whole thing to a more like axisymmetric state. So this is like between for the first tens of milliseconds or so. This is where gravitational wave emission probably through the oscillation mode is probably strong, very strong, and sort of drives the object to a more axisymmetric state. But once it's in this axisymmetric state, gravitational wave emission will essentially cease, and then the spin down actually takes over, and this can then take over for a spin-down timescale, meaning for up to days.
But then I just move on because
sure, we can.
Very, very briefly, if the internal field is 100 times stronger than the external dipole field and it's misaligned, it will spin down faster because of that distortion from gravitational waves than from electromagnetic. But it does have to be. We have a much stronger internal field to like sort of change the shape of the star. That's not modes. That's just like just a non-spherical distortion.
This depends on which kind of gravitation.
Yes, there's different. Our modes are not that much stronger.
Can I ask one more question on this topic? So you said that in this time reversal scenario that the short GRB would emerge when the neutron star collapses to form a black hole. What I missed is what actually happened during that collapse that causes the short GRB.
Okay. Yeah, very good point. So I'm looking at Ben. Brian's laughing. So this is what I was not mentioning. So of course these alternative scenarios, they don't come without problems. I mean, they also have their own problems, and especially this one also has a problem, namely that we sort of assume that during this collapse, you form a black hole that you essentially form a black hole, and what we have to assume is that still significant amount of matter still ends up outside the horizon during this collapse process. So that you can actually have something like an accretion disk that accretes onto the black hole and forms a jet. Now there's work by Ben, who's here in the audience, and Brian and others who have actually shown that this is actually fairly unlikely to happen. So we're not really sure if say uniformly rotating, or say more or less uniformly rotating neutron star of that kind can actually produce a black hole torus system when it collapses. But this is something that we should also further investigate with also the simulations.
Okay. So it might not even necessarily be would it necessarily be a short GRB as opposed to?
Well, in this case, yes, probably, because the typical timescales for accretion of such a torus would be on the short short GRB.
So if you did make a torus, it probably would be
Yes.
short GRB, but it may be really hard to make a torus
Yes.
from a solid body neutron star.
Okay, before we are standing between the wine and people, we should talk about everything. So Kota, why don't you go ahead?
Yeah, actually, it's around the same line. So this is a kind of the configuration for it's a case called a supernovae, and actually Brian and people actually try to explain the connection between the superluminous supernovae and GRB and perhaps HRB using the parser. And then the scenario is as follows. So that if you put the parser, the pointing flux is dissipated for the non-summer radiation, and then the ejected non-summer radiation, fraction non-summer radiation is converted to summer radiation, and then it's ejected sick, and then you can use or shock, and then you can expect that the significant summer emission from the parser-during supernovae, and then. But if you wait for a long time, eventually the ejector starts to, be seen, and in this kind of scenario, I think that it's quite natural to expect that no summer emission, because this is assumption is as follows. Of course, at the earlier stage, we are not sure how the magnetic field dispersions goes, right? But if you look at the galactic parts of wind nebula, and then we know that the most of the pointing energy is dissipated for the northern pattern. Let's take this assumption, and then if you extrapolate this physics to the early phase, and then it's natural to see expect the northern signatures. And then just by adopting this assumption, you can calculate the northern signals, and just you can predict actually by fitting the supernova light curve. And then you can determine the parameter space and the spin down time as the period, the magnetic field, and the ejector mass. And then you can try to calculate the radius and the X-ray emission. Yeah, I think that usually the X-ray emission is very strong, but also affected by the absorption in the ejector. And I would like to point out that the radio emissions can also be interesting. And because if you wait for the couple of years, 1 year or 10 years, and eventually the system becomes transparent for the free absorption or single absorption, and then for the nearby supernova or nearby superluminous supernovae, then it starts to be possible to see some characteristic radio signals from this kind of nebula. And this is, I think that this is especially powerful at higher frequencies, such as the sub-megahertz frequencies, because you can avoid a free absorption. And then, for example, if you make a follow-up observation with Varma, it's possible to see the radio signature.
What do you mean by GWFF?
Oh, this is I'm talking about later. Then actually, this is one slide. This is actually Brian mentions that in principle in the early phase, and then here another assumption is that that I basically try to explain this superluminous supernova, several these stripped embryo supernova using the spin down power of parser. But in principle, for example, there are many possibilities. But if, for example, if the internal field, toroidal field is so strong, and the neutron state is distorted, and you can achieve the situation where the gravitational wave loss, energy loss dominates in the early phase. And in this case, actually, of course, your spin down power is reduced, and the optical radiation is suppressed, and later emission is also suppressed. And in this case, it's good for the gravitational wave detection, but actually you have the anti-correlation between the electromagnetic signature and the gravitational waves, of course. And then I just demonstrated this, and then if you ignore the effects of such a gravitational waves, and it's actually easy to find the parameter space to explain the superluminous supernovae using the spin down timer. But if you put the strong magnetic field, for example, if the distortion parameter is around 10⁻⁻3, and then or a few times 10⁻⁻3, and then early magnetic gravitational wave loss start to be important, and then it's very hard to find a parameter space to by which you can explain supernova.
But it is not good news for the gravitational wave because these are not gravitational waves that can be measured. The time delay, the time scale of this gravitational wave emission is much longer than, so the luminosity is much longer, so it's bad news for everybody.
It's bad news for everybody. But it depends on this parameter, right? If you put the strong weight, actually.
Yeah, if you put epsilon to 0.1, then you will get some.
Yes.
But with 10 to the minus 3, you will not get the detectable gravitational wave signal.
But you have to be, of course, even the 3 times 10 to the minus 3, you need to see the signals very nearby. I think the only bug, you need to put a bug, yeah.
For the most optimistic one, what would be the reflection rate?
Well, if you consider supernova, no. So that basically, it's very right. You can proceed. But it depends, right? Because in general, if you take if such a thing happens in the usual contour of supernova type 2, I cannot exclude such a possibilities. You could expect 1.2 years, right? It's bad.
Yeah. Okay. Yeah. Very good. Very good. Okay. Thank you. Maybe let's move on. David, you want to add something? What has not mentioned that is interesting?
I can say a few things. I was asked to answer the question whether observations can help simulations or the other way around, which is a very nice question. I think, the goal of observations should be to help simulations for sure, because
Of course.
simulation should be a tool towards understanding the observations. More seriously, there are things that actually will make our lives as simulators easier if we learn them from observations. For example, if we can rule out the presence of other physical effects, for example, like nonlinear tides in the inspiral, the impact of, for example, a Poynting flux rebrightening the ejecta in the modeling of Kinova. These are kind of things that are very difficult to model in simulations, where we might actually get a handle on already from the observations using simple models. So this is one part of the answer that I would give to this question. The dual answer is what needs to be done in simulations now in order to help observations. I think there are two important things that simulations should do and will do in the next few years. One is modeling the post-merger emission of gravitational waves better. It's something that we have discussed a little bit before. I think that we're still a long way before we have gravitational wave signal we can trust to the phase level accuracy. So we cannot really do much filtering with what we have now. And the other thing that we should try to understand using simulations is whether all binary neutron star mergers make a short gamma ray burst, which is also something that has been discussed this morning. And here I think one interesting thing that we have to ask ourselves is if only a fraction of neutron star mergers make a short gamma ray burst, what is special about them? And can we, by looking at simulation results, can we identify there are families of solutions? For example, I don't know, if for some equation of state 20% of binaries make short-lived remnant. We know from observations that only 20% of binaries should make gamma ray bursts. What does this tell us? So this is, I think, the kind of questions that we have to address with simulations. But more in general, I would be happy to hear what you as a community want our simulators to compute.
Would
so
you?
The question that you meant, so there is a degeneracy between, so this is something I didn't know. I thought
yes,
either you produce or you don't produce electromagnetic observations. You're now saying, okay, there may be a fraction of these binary neutron star mergers that don't produce anything. But then that is degenerating with the angle. You don't know whether you're not observing it because they don't emit or because, are you talking about the EM afterglow or are you talking
I'm talking about, I mean, we have always assumed that if you merge two neutron stars, you always make a gamma ray burst, but I don't think this has to be necessary.
So that, yeah, if that is the case, then I think that is completely degenerate with the beaming angle.
That is true. This is why we need better simulations.
So I would say that is very
which fraction of
yeah.
neutron stars are peculiar, for example.
Yeah, it would be very helpful to understand that problem.
Yes.
One thing, you say that if you, for example, are informed by observation, then you can go and simplify or tweak your code to reproduce what you're observing. I think that would be a bit dangerous because you have one sample out of a big parameter space.
Yes.
And if based on those